I'm going to draw a little cell here for us. This cell is going to be a typical cell, and it's going to be full of potassium. We know that cells love to hold on to potassium. So let's draw lots of potassium in here. And the concentration of potassium, let's say, is something like 150 millimoles per liter. So that's a lot of potassium, right? And I'm going to put brackets because brackets indicate concentration. And of course, there's some potassium on the outside too. Let's say the concentration here is something like 5 millimoles per liter. And I have to also show you how this concentration gradient gets set up, right? It's not like it just happens to be set up. It's something that we put a lot of energy into creating. So you get 2 potassiums pumped in, and you actually kick out 3 sodiums. So that's how you get all those potassiums in there in the first place. So now that they're in there, are they hanging out by themselves? The answer is definitely no. They are finding anions, little negatively charged molecules or atoms to sit next to. And so the net charge is going to be neutral, right? Because every cation has an anion. And usually these anions are things like proteins. Something that has maybe like a negative side chain, like a protein, could be a chloride, could be phosphate, could be a number of things. So any one of these anions would be fine. And actually, let me draw a couple of anions here as well for these 2 potassiums that just got welcomed into our cell. And so this is how things look. You know, if things are nice and static, this is how they look. And actually, to be quite honest, there's also a little anion hanging out here as well for this potassium. So now the truth is that we have little gaps in our cell, little holes, where we allow potassium to actually leak out. So let's actually show how that would look and how that would affect what's going on. So we have these little channels, and they only allow potassium through. So these channels are actually very specific for potassium. They're not going to allow any anion through or any other thing out. The protein certainly can't get out. And so these potassiums are kind of looking at these channels that are there, and they're thinking, this is interesting. There's a lot of potassium in here. We're going to want to just, slip out. And so these potassiums just kind of bail on the cell, and they just get right outside. Now, when they do that, an interesting thing happens. Most of them move outside, but there are some potassiums outside as well. I said that there was this one little fellow over here, and he could theoretically kind of make his way in over here. He could, come into this cell if he wanted to. But the truth is, overall, on the whole, on net, you have more movement outside than you do inside. And so I'll just, for the time being, erase that path. Just because I want you to remember that overall, we have more potassium that's going to move outside because of the concentration gradient. In fact, that's point number 1. So actually, let me write that down here. Concentration gradient is going to make the potassium move outside. And that's on net. So the potassium starts moving out, right? So K out. And what happens next? Well, when it moves outside, let me actually draw it moving outside. So this K is now over here. And this K is over here. And what it's left behind is an anion. In fact, this guy's left behind an anion as well. And those anions, they are all by their lonesome, they start generating a negative charge. A big, big negative charge. Actually, just a few ions moving back and forth will create a negative charge. And these potassiums on the outside, they're thinking to themselves, that's interesting. There's a negative charge in there. And if there's a negative charge in there, they're attracted to it because they're thinking, well, I'm positive. This is a negative charge. I want to go back inside. And so on the one hand, think about it. You have a concentration gradient driving potassium out. But on the other hand, you have this, what we call membrane potential, in this case a negative one, a membrane potential that gets set up because the potassium has left behind an anion. That's actually going to drive the potassium to want to be back inside. So you have one force, the concentration driving K out, and another force, the membrane potential that gets created by its absence, that's going to drive it back in. So I'm going to actually make a little space here. I'm going to show you something that's kind of interesting. So let's create 2 curves. Let's say we have, actually, I don't want to lose everything on this slide. Let me actually just set this up here so So you can see the last little bit of it. So let's set up two curves. One will be for the concentration gradient, and one will be for the membrane potential. So this is, let's say, K out. And you actually, if you followed it over time, this is time, you'd actually see that you actually have something like that. K is actually going to move out over time, and it's going to, at some point, get to an equilibrium. And if we did the exact same thing with time on this axis right here, and let's say this is membrane potential, and we start at time 0, and this is also negative axis, so this is going more and more negative this way, and we start at 0 for the membrane potential, and this is at the point where you start letting the K kind of wander out, you get something like this. Basically looks the same, but is kind of a parallel of what's going on with the concentration gradient. And when the two equal each other, when the amount of K moving out equals the amount of K moving in, we get to this kind of plateau. And it turns out it's about negative 92 millivolts. So that's the point where you really have almost no difference in terms of the net movement of K. It's equal. And in fact, we even call that term, we call that the equilibrium potential for potassium. So when you get to that negative 92, and it differs depending on the ion, but when you get to the negative 92 for potassium, you've hit its equilibrium potential. So let me just write that out. For K is negative 92. And again, this is assuming that the cell is only permeable to one thing, which is potassium. Now, this actually might still bring up a certain question in your head. You might be thinking, and I want to make sure I address this, well, wait a second. If potassium ions are moving out, and that's what I said is happening, then at some point, don't we have a lower concentration in here because the potassium is actually left, and a higher concentration out here because, potassium is moving outside? And technically, that is correct. I mean, of course, you have more potassium ions on the outside, and, I haven't said the volume has changed, so yes, you would have a higher concentration. And the same is true for the cell. You'd have a lower concentration, technically. But realistically, I haven't changed the numbers, and the reason I haven't changed the numbers is because if you look at the numbers, these are moles. I mean, this is a huge number, right? 6.02 times 10 to the 23rd. That's not a small number. And if you multiply it by 5, then you get something, this kind of works out to about, I'm going to quickly do the math, 6 times 5 is about 30, and then you got millimoles here to consider, so about 10 to the 20 moles, right? I mean, that's an enormous number of potassium ions. And really, you just need a handful of ions to create this negative charge. So if only a handful of ions are moving back and forth, you're not going to really make a difference to that enormous number, 10 to the 20th. So that's why we don't really think of the concentrations as changing very much at all. So in the last video, we talked about how you have a higher concentration of potassium on the inside, around 150 millimoles per liter, than you do on the outside, let's say around 5 millimoles per liter. So, and just to recap some of the kind of important points we brought up, we said that essentially what happens is that you have these potassiums that are bound to little anions that are the green dots there. And because the concentration gradient is going to want to make the potassium leave the cell, it will. And so it'll leave the cell. Let's say this little fellow will leave the cell here, and he'll end up on the outside. So by doing that, he leaves that anion all by itself. And if this continues to happen, then these anions create this negative charge, and we can actually figure out exactly what that negative charge is. It turns out that that negative charge is going to attract back the potassium, right? We said that this potassium then is going to want to kind of swim back inside to be closer to that negative charge. And this is kind of that interesting idea, the idea that K leaves behind a negative charge and then comes right back and wants to be by that negative charge. And the amount of negative charge that's going to offset the concentration gradient is around negative 92. So let me write that in now. So negative 92 is the amount we know that we need to kind of offset the concentration gradient. So that's where we left off. And now I want to do a little thought experiment. Let's say that we come at this cell with a little injection full of, let's say, some positive charge. And try to ignore the kind of ridiculousness of what I'm saying just for the moment. But just focus on the positive charge, the fact that I'm going to pour a bunch of positive charge into this cell. And let's assume that we don't know exactly where this is coming from, but that this positive charge is essentially what it's going to do is it's going to make my cell not negative 92 anymore, right? It's going to make it more positive than it is. Let's say I make it, let's say halfway back to 0. So instead of negative 92, it's negative 46 millivolts. So this is the new membrane potential, right? And our cell is still just permeable to potassium, and that's really important. It's only permeable to one ion, that's potassium. So what's going to happen? Well, these potassiums, these little guys right here, they're going to notice that the charge is actually not drawing them back as strong as it was before. So this potassium might see that and it might leave. And so more potassium basically starts leaving the cell. And if more potassium is leaving and kind of going on the outside, then you have more of these little anions that are left behind, and the process continues, right? So these anions say, well, if we're off by ourselves, we're going to contribute to this negative charge. We're going to add to it just as it did before. And that negative 46 is quickly going to go down again. It's going to slide back down. And the question is, how far does it slide down? Well, it goes back to the equilibrium point. So if we said negative 92 is what you need to make this yellow squiggly attraction, the membrane potential, equal the concentration gradient, if that's what's needed, then it will slide back down to negative 92. So think about that for a second. It's pretty powerful stuff. I mean, you can do all sorts of kind of funky things to the cell. You can add positive charge or negative charge. And as long as you maintain two important things, one of them being the concentration gradient. So one is this concentration gradient of 150 versus just 5. That's one thing. And the other is the permeability to only potassium. As long as you maintain the permeability, you'll get back to negative 92. So actually, let me even hammer this point harder by showing you a little diagram. So let's say we have a concentration gradient over here, and I also have permeability over here. Permeability. And this is permeability to potassium, okay? And assuming that we only have permeability. So assume, I'll write that very clearly, the cell is only permeable to one ion, only one ion. So assume only one ion for this permeability. So if you have, let's say, permeability yes and permeability no, and you have concentration gradient yes and concentration gradient no, then what do you get exactly? So let's say you have 4 possibilities here, right? We have 4 possibilities. And let's say we have no concentration gradient and no permeability. Would we get a membrane potential? Well, no, because the potassium would never have a way of leaving in the first place and would have no desire to leave. Now, what if you have concentration gradient, so you have the desire to leave, but you don't have a way for that potassium to actually leave the cell? Well, again, you don't actually have any membrane potential. And the same is true as if you have a permeability, but you have no concentration gradient. Then the potassium, again, has no desire to actually leave. And then finally, if you have permeability and a concentration gradient, then you actually get down to your negative 92 millivolts. So concentration gradient is kind of when I use the word desire. Does the potassium have a desire to leave? And permeability is, does it have a means? Does it have a way to leave? So these are the two things to kind of think about when you're thinking about whether you would create a membrane potential or not. So if we have that set up, let's actually move down a little bit, make some space, and actually talk about how you actually get your negative 92. Where in the world does that number exactly come from? So there is a formula, and that formula is, I'm going to write it out over here. It's Vm, and all that means is membrane potential. Now, if you're like me, the first thing you notice is that there's no V, there's no letter V in the word membrane or potential, so how do they come up with that? And I don't know the answer to that. I don't know where the V comes from exactly, but Vm stands for membrane potential. And the formula is actually surprisingly simple. It's 61.5, and this is kind of a simplified version because there are a lot of constants in here that get kind of thrown together in that 61.5. And you just take the log of the concentration of potassium on the outside, I'll say K out, potassium on the outside, over the concentration of potassium on the inside of the cell. So you take these two concentrations and you get this fantastic little formula. And you can actually, now I can write for you potassium over here we said was equal to negative 92 millivolts. So that would be the membrane potential. This is the membrane potential. And I can even walk through a few other ones, some other key ones. So there's sodium, there's, let's do chloride and calcium. So a few of them. And all of them have the same kind of formula. You just take their concentrations on the inside and outside and plug it into the formula, and you get positive 67 for sodium. You get negative 86 for chloride, and you get positive 123 for calcium. And now, keep in mind, calcium has a 2+ charge. So for calcium, this 61.5 actually gets changed to 30.75, and that's rounded off, but that's because of that 2 positive charge. And all you do is, as I said, throw in the concentrations on the inside and outside. So actually let's even write that down. So concentration gradient, and keep in mind exactly which way things are moving. So concentration gradient for potassium, I mean really you're looking at a positive ion, right? That's moving out of the cell. And for sodium, you have a positive ion, but it's moving into the cell. For chloride, you have a negative ion moving into the cell. And for calcium, you have a positive ion moving into the cell, really just like sodium. So this is how you kind of can think about the 4 major ions that contribute to our cell's membrane potentials.